Hello students, welcome back. Essentially, we completed lesson 1. All that's left is some demonstration or some motivational videos. Why are we doing this? Why vectors? Please recall that a vector can be written as a pair of real numbers, x, y, where x and y represent x-coordinate and y-coordinate. Now consider those as functions of another variable, let's say t. Then x of t and y of t become both functions, and the best way to visualize it is through a position vector or position vector function. X of t is horizontal position and y of t is a vertical position in a coordinate plane where t is a time variable. Basically, you're getting something like this. Let's suppose we have x-axis like this and y-axis like that. And then x of t, y of t is horizontal and vertical position right here at a certain time t. And as t changes, as time changes, the position changes. So what did he end up with? Starting from here, and this point moved around and formed a curve. So trace of this motion became a curve. Now calculus has a lot to do with motion, the change. Geometry is just a picture that's static. Calculus is dynamic. So we are far more interested in functions and their behaviors here. And of course, if you put together x of t and y of t, then you get two-dimensional curve. If you put together three functions, x of t, y of t, and z of t, then you're going to get something similar in 3D space. It's a little bit difficult to visualize, but please use your brain. All those can be done using calculus, and that's basically what we are studying for this course. Let's erase all that. And then let's go ahead with some further applications and examples. Here's a simplest example. P of t is given like this as a linear function. X of t is a linear function, x0 plus at. Y of t is another linear function, y0 plus bt. And it's supposed to be a line. Well, no surprise there. Both x, y are linear functions. As a matter of fact, you get something like this. Let's see. P of t minus p0, both are position vectors, equal to tv, scalar multiplication. So that means this one here, the left-hand side, which the left-hand side here, which I'm highlighting in purple, is parallel to this v, which I'm highlighting in blue. Excuse me, sorry about that, wrong key. Okay, all right. So what does that mean? It means this. So P of t minus P0 is actually this vector. Oh, this is bad. Let's try again. This kind of vector. Let's see. P of t, that's arbitrary point on this line, this purple line, and if you consider that from the origin, it's going to be like this one here. So P of t, which I just highlighted in red, is actually this vector starting from the origin as a position vector from the origin. But if you take P of t minus P0, you see P0 is this one black. Then black plus this purple is this red. So purple is this red minus this black, so that you get this. So if you look at this purple alone, that's parallel to this blue. And that's for arbitrary point here. This point 2 and this point 2, anything on this line. A bit difficult to see, I don't blame you. So instead of the static picture, let me show you an animation. Okay, I don't need this picture anymore. Now look at this. So do you see this red arrow moving around? This red arrow is P of t, the position vector. Let's stop this. So that's the red vector you're looking at. And then P0 is this black vector. And if you subtract, black. So red minus black, if you subtract one from the other, you get a purple vector from P0 here to the tip of this red arrow. And that red arrow will change because it's a vector function. It depends upon time t. Now, if you solve for this red, then this red vector, P of t, is P0, this black, plus t times v. V is this direction, times t, so parallel, so any time t. So t can be large, so it can go farther to the right, or t can be very close to 0, in that case, very close to this black point. If t is negative, you can go to the left. And then you can consider this as time t. So in past, a point was here, and it is moving, and then at starting point, starting measurement at 0 right here, and then in the future, the point will move further to the right. And then if you express all those in terms of coordinates, that's what you're getting. x0, y0, that's this black point, and t times AB, in AB, that's a blue vector, the direction vector. And then x0 plus TA, that's your x coordinate, x of t, and y0 plus tb, that's your y coordinate, y of t. And that's what you're looking at here. Okay, that was one example. And there are more examples, but the other examples will be a lot quicker because they are more complicated. In this case, you're going to get an ellipse. P of t minus P0, again, it's a vector starting from this P0. So this P of t minus P0 is vector starting from this P of t, and that's going to move around like this. Like this. And then the trace will turn out to be an ellipse. Everybody went through trigonometry, so a cosine of t, b sine of t, or more easily, just cosine of t, sine of t will become a circle, that much is certain. But we have a and b values, so stretched horizontal and vertically a little bit different. Consequently, we get an ellipse instead of circle. If a and b are the same, then you're going to get circle, or radius the same constant. but A and B are different, then horizontally and vertically, they are squished and stretched differently, so we get an ellipse like this. Now, let's look at something more dynamic. So that looks a little bit more like a circle. And these foci are too close to each other. Let's run this again. Okay, that's a little bit more squished. All right, that's better. And here is the animation associated to this. So P of t is a position vector, and that's the red vector, and that's moving around. And so for P of t, then we get P of t is P0, the center, plus A cosine of t is B sine of t. If this had been just R cosine of t, R sine of t, then that would have been a circle. You know, everybody went through trigonometry, so cosine comma sine will become a circle. Everybody should know that. But instead of same radius R, we have two different radii, A and B. So horizontally stretched by A, vertically stretched only by B. And in this case, A is bigger, so we get an ellipse stretched horizontally. Let's see, this program is randomized, so if I run it again, maybe you're going to end up with, oh yeah, in this kind of a case, B value is bigger, so we have an ellipse stretched more vertically. So vertically 2.88 something, horizontally 2.6 something, so vertically stretched more, so we have an ellipse this way. Okay, so much for conic sections. Here are even more complicated curves. This time I'll just show you a picture. And I have both x and y coordinates with sines and cosines only, and they're all periodic. So there's no surprise that we have a closed curve. But this closed curve, well, that looks pleasing aesthetically. So I took this example. I named it a flower because this reminded me of flower. Anyway, here is a, oh, too quick. So this red point is moving around. You can consider it as just a point or a position vector, which is the arrow. And then the trace of that moving point is the curve here, which I named as flower. And both x and y coordinate are functions of time, t, but they're all sines and cosines, they're all periodic. So we get a closed curve. Interesting example and aesthetically beautiful. Here's another example. This one I named it a butterfly. Okay, here we go. And this kind of motion is associated to the behavior of this x function and y function. How do you analyze this motion, the dynamics? Well, that's basically what we study in calculus. Of course, we're going to begin with a function that is far easier than things like these. But these kind of complicated functions are not completely out of reach. We will study those kind of things in this course, yes. Alright, so much for lesson 1.